Welcome to Mastering Solutions. In this problem, we'll be discussing impulse and momentum again. And with this problem, it's really beneficial to draw a picture at the beginning because it really will help you later on in the problem. So they tell us that we have a tennis ball and the ball is getting thrown towards the wall. Now, just because of convention, we're going to say that the velocity, since it's a vector, is going to be a negative value since we're going in the negative x direction. It hits the wall and then it rebounds with a force, and then the ball bounces off, and when it's going in this direction, we have a positive velocity. So they give us a graph over here on the side. So we have force on the y-axis and milliseconds on the x-axis. So next, let's go through and write down our variables to the problem. So they tell us that the velocity initially is 32 meters per second. And remember, because we're going in the negative x direction, the initial velocity is negative. They tell us it rebounds with the same speed. So our final velocity is going to be a positive 32 milliseconds. The mass of the ball is 60 grams, but we need that in kilograms. So we're going to be moving the decimal place over 3. So 1, 2, 3 gives us 0.06 kilograms. So 1, 2, 3, perfect, 60. And of course they say, what is the value of Fmax? Now we know that we're going to be, we're going to be using impulse. So let's write the impulse equation. So J is equal to the change in momentum, which of course is P final minus P initial. Now what we're also going to be using here is a different way to find J is the area under the curve. So we need to find all of this area here, which will also give us what the impulse is. So to do this, we're going to find what the area is of this triangle right here. And then we have this triangle right here. And then, of course, this square. So J is going to be equal to 1/2 the base times the height for the first triangle plus the base times the height for the square, and then 1/2 the base times the height of the second triangle. So now if we pull out the h of all these, J is equal to h times 1/2 base plus 1/2 base. So for this, the h that we're referring to, the height, is the Fmax, and the base is the change in time, which of course, as we know, is also Fmax times the change in time is the other definition of impulse. So when we plug in our values into this one right here, we have J is equal to h times 1/2 of, from here to here, we have 2 milliseconds, here to here 2 milliseconds, and here to here 2 milliseconds. So 2 plus 2 plus 1/2 of 2, which gives us h times half of 2 is 1, half of 2 is 1, plus 2, so 4. So we're going to be multiplying h, or Fmax, by 4 milliseconds. So let me rewrite this just to be really clear. So J is equal to Fmax times the change in time. And we said h is the Fmax and the base is the time. So we just found J is equal to Fmax times 4 milliseconds. So we want to isolate Fmax. So if we divide both sides by change in time, Fmax is equal to J divided by 4 milliseconds, so 4 times 10 to the negative 3 seconds for the change in time. But we don't know what J is, right? So we can't find Fmax without solving for that. So we have to come back to our equation up here and use the change in momentum to find the J to plug it in. So if we come here, we have J is equal to P final minus P initial. And we know that, like we just talked about, that that's also equal to F max times the change in time. So really, we could even skip this step over here and just plug this in for J. So if we divide both sides by a change in time, over here, F max is equal to P final minus P initial all over delta T. If we keep going, we have mv final minus mv initial all over the change in time. So we're almost there. F max, now we can just plug everything in, is the mass is 0.06 kilograms times the velocity of the final is a positive 32 meters per second. Then we're going to minus a 0.06 kilograms times a negative 32 meters per second. So this is where the picture saves us, because if you don't do that, you'll get the incorrect answer. We're going to divide the whole thing by the change in time, which we said was 4 milliseconds. 4 times 10 to the negative 3 seconds. 0.06 times 32 minus 0.06 times a negative 32, all divided by 4 times 10 to the negative 3 seconds, which gives us a F max of 960 newtons.